Here I have listed out certain checkpoints that you would consider when you are selecting a embedded microcontroller, and they would be whether your microcontroller has peripheral features, whether it has enough memory for your application. What about the packaging? Because packaging would be an important consideration. Is it available in the package that you want, because your application may not offer too much physical space. ICs are produced in many grades. A commercial grade is the most common grade. This is used for commodity consumer products. Typically, the temperature of operation of such ICs is in the range of 0 to 70 degrees. Industrial temperature range is higher than that. Automotive is even higher, and military grade components operate at much wider temperature ranges, because that is what they expect in a military application. Then you would look at the price, availability and lead time. But an important component is, since you are going to use a microcontroller in a real time application, where it is going to sample external parameters such as temperature or sound, therefore, it must be able to sample that signal appropriately. And whether a particular microcontroller is up to the job or not is determined by the maximum frequency component of that external signal. Let me take two examples. If I am looking at regulating the temperature of this room using an air conditioner, I would need to know what is the temperature of the room. So, I need to sample, that is, I need to connect a temperature sensor and digitize the value of this temperature sensor every few seconds. That is enough, because the room temperature is not going to vary very fast. On the other hand, if I want to look at an application such as the noise cancelling headphone, then the noise cancelling headphone has to sample external sound. The maximum frequency of the external sound is 20 kilohertz. We can't hear beyond that. So, we must sample 20 kilohertz at an appropriate sampling frequency, and I have illustrated that here, that the time between two samples, we call it inter-sample interval, and this would vary from application to application. Like I mentioned, for measuring temperature, the inter-sample interval will be very large. For sampling sound frequencies, if I am going to sample a 20 kilohertz signal, I must sample it in keeping with the sampling theorem, Nyquist rate, and I have to sample that signal at least twice the maximum frequency component. So, a 20 kilohertz signal, a signal which has a maximum frequency component of 20 kilohertz, must be sampled at 40,000 times per second at least, and so you would sample it probably at 45,000 samples per second, which means the time between two samples is going to be less than, I would say this is about 20 microseconds. Is that right? Yes. Therefore, what happens in these 20 microseconds? At this point, the microcontroller receives one sample. After 20 microseconds, it is going to receive one more sample. It must process the current sample that it has received here and produce an output before the next sample is due. Now, we have taken three cases. Let us say we choose a microcontroller of type A. If the program that runs and processes this sample, it would, and if it takes more than 20 microseconds to complete this task, it is not suitable for this application. How can we still make A usable in this situation? Maybe we can increase the clock frequency so that the resultant time is B, such that it is less than the intersample interval, then it may be a marginally acceptable solution. If we can increase the clock frequency even more, that is the internal clock frequency of operation of this microcontroller even more, such that it takes less than half the time, then it is a very comfortable situation. In case you are not able to bring down the processing time to less than the intersample interval, you may be forced to replace this microcontroller with a microcontroller which offers you higher performance. And before you do that, you would consider can I increase the clock frequency of operation so as to manage the completion time of the sample before the next sample is due. And so therefore, the value of the clock frequency is very important when you are looking at physical signals which have to follow the Nyquist rate. Let us look at the next aspect of the ecosystem, which is the reset. A microcontroller requires a reset signal. Why does it require a reset signal? Well, the answer is very simple and obvious, that a microcontroller has a CPU. A CPU has a control unit. A control unit utilizes flip-flops, and the values of these flip-flops, they are important. When you apply power to the microcontroller for the first time, you want these flip-flops to start with a known state. Similarly, apart from the control unit, you have an important register in your microcontroller or microprocessor, which is the program counter, also sometimes called instruction pointer. So, let me write them here: program counter or instruction pointer. This is nothing but a few flip-flops arranged together to provide the initial address when the microcontroller is reset, right. Now, if the value of these flip-flops take arbitrary values, that would mean that after reset the microcontroller at some point may go to a certain memory location to fetch the first instruction, at some other time it may go to a different location, and if that happens, you will never be able to execute your program properly. All microcontrollers require that after reset a fixed location, a known location is accessed to access the first instruction stored in the memory. In many cases that address is 0000, say, or another 0 if you like, this address. So, this address must be output on the address lines connected to the program memory. If you do not reset, initialize the flip-flops that make the program counter or instruction pointer, then it may emit arbitrary values on the address bus, and it would be a very chaotic situation. So, to ensure that every time power is applied to the microprocessor or the microcontroller, it starts with a known state, internal state of the computer, it is very important that you reset. Why? Because we know that a flip-flop is represented with these signals. Say a D-type flip-flop would have D input, a Q input, Q output, a clock signal. This is the very minimum signals that you require, but it will also offer you a reset, which when asserted will reset the value of Q to 0. It may also offer a signal called set. If you assert set, that will make Q equal to 1. And so, when you use such flip-flops to create various registers, the reset or set signals are utilized together by the control unit so that they can be initialized with a known value. And therefore, this act, that when the microcontroller is applied power for the first time, the microcontroller start with a known state, this is called resetting the microcontroller. So, we see why we need a reset, so that our system is going to start from the known state each time, every time. Now, there are many sources of reset. One of them, as I mentioned the term, that every time you apply power to the microcontroller or microprocessor, it should reset itself without having to be prompted, and such a source of reset is called user reset. We will see other sources of reset, but before that I have classified the resets to be of two types: warm reset and cold reset. A warm reset means that the system power has not been disabled, it has not been switched off, and you would still like to reset the system without turning the power off. Other source of reset would be a cold reset, meaning you turn the power off and when you turn it on again, it would be classified as a cold reset. Of all the resets that are available, and here is the list of those resets, you have power on reset, which I have discussed, that is a reset signal internally which is generated when you turn power to a microcontroller system, that is called power on reset. Another reset source is the user reset source, and let me show you in the next slide. Here if you look at the pinout of these devices, you will notice that on pin number, if you see here, this is a reset pin of this AVR microcontroller, and on this MSP430 microcontroller you have a reset signal somewhere here. And these pins which are designated as RST bar or RESCT on these two microcontroller refer to the user reset, meaning a user can assert a logic level on these pins and it would reset the system even if the power supply was not taken off, even if the power supply was applied. And usually the way to do that is you would on these pins RST bar, you would connect a switch. So every time you want to assert a user reset, the user simply presses this switch, it pulls the reset pin to ground, this resets the internal circuitry, and when the switch is released, it would allow the circuit to reset and then it will start performing its expected task. The third type of reset is called BOD. BOD stands for brown out detector. So what is a brownout condition? Because you have a detector which detects brownout condition. Brownout condition is that if this is my, as a function of time, this is my VCC, that is the supply voltage. If at any time it dips below a certain level and for the entire duration of time that it remains below that threshold, again rising to expected levels, if it has fallen below this threshold here, then this may be detrimental to the operation of the processor. It may corrupt some register values, it may write wrong values into flash memory or EEPROM if the controller was performing some write operations, and it may be better to reset the system rather than go ahead with this corrupting activities. And this is where the brownout detector plays a role. If this brownout detector has been enabled, then it would generate an internal reset which will hold the internal circuit in microcontroller in a perpetual state of reset till the power supply voltage level resumes and exceeds the minimum threshold that is required. Let me explain the operation in using an external circuit. Suppose you had you take a comparator, and I would have minus and plus signals of a comparator. It would have an output. It would, here what I will do is, it is also powered with a power supply, say VCC, which is the power supply of your microcontroller. I am going to take a voltage divider made out of two equal value resistors, and therefore the voltage here would be 0.5 VCC if both these resistors are of equal values. Let us say that VCC is 5 volts, therefore the voltage that you expect at this point when the supply voltage is 5 volts will be 2.5 volts. I take another little circuit using a resistor and a reference voltage diode such as a Zener. I connect it to the positive input, and let us say this is 2.25 volt reference diode. Now as long as the power supply is 5 volts, the input is going to be 2.5 volts and therefore the output here is going to be 0. But at any point of time, if this power supply, instead of being steady at 5 volts, instead of that if it falls to a low value such that the voltage here becomes less than 2.25 volts, the output here will go to 1, and this signal could be used to reset the internal reset circuitry of the microcontroller and hold it in reset till such time the voltage resumes back to the normal values, or at least exceeds above the threshold at which the brownout detector kicks in. So, this one can think of such a circuit that has been integrated inside the microcontroller, but it functions in this way that I have illustrated using op amps and couple of resistors and a reference diode. So, this is how a brownout detector works internally, and one has to be aware that their microcontroller offers such features, and in case they expect the power supply to be show such a behavior where the power supply voltage is fluctuating, then they should enable the brownout detector so that their entire system keeps on working properly. The fourth type of reset source is this what is called as watchdog timer, and watchdog timer is a common feature these days in microcontrollers. As the name suggests, it is like a watchdog at home which would start barking if it finds anything other than usual intruder or something like that. In a microcontroller system, if the program gets stuck for whatever reason, the watchdog timer could be used to redeem the system to come back out of that stuck situation and start operation again, and a simple way would be to reset it. Unfortunately, if the system is out of human reach where it cannot be manually reset using the user pin, then the only way would be to use the watchdog reset. And let me illustrate again with a small circuit diagram how it works. So, imagine that you have a counter, and this counter can be fed with a clock source, and let us say it is an independent source of clock, and let us say this is a n bit counter. So, it would count 2 raised to power n clock pulses, at the end of which the overflow pin of the counter, let me write it completely, pin would become 1, and if this becomes 1, it can be used to reset the system. Now, obviously, you do not want this timer, this is your watchdog timer, you do not want this watchdog timer to overflow. So, how do you ensure that it does not overflow, because that overflow situation is going to reset the system, is that any counter can also have its own reset. Let us call it C reset, that is counter reset, and this pin could be connected, is actually part of a register, and the microcontroller program would periodically. So, if I know that 2 raised to power n into the clock frequency here, T, I will use a name so that it is not confusing with the clock frequency of the system, WDT, watchdog timer clock frequency. Let us say this is a 1 megahertz clock, so therefore, it is a 1 microsecond time period. Let us say n is 16, therefore, it is 2 raised to power 16 clock pulses required to overflow this. This is about 65,536 clock pulses. So, roughly this will give you a 65 millisecond period within which, if you can reset the timer, it will not reset you. If you forget to reset it for whatever reason, that imagine that the program has stuck and cannot reset this timer, then the timer will overflow and it will then reset the system, bringing back sanity into the system. This is how a watchdog timer reset works. So, we have seen at all the various ways of resetting the microcontroller. Now, let us move forward. This I already illustrated the user reset pins on two popular microcontrollers. The other aspect that you require as part of the microcontroller ecosystem is the ability to download program from the development setup into the memory of the microcontroller. And I am going to go through a little bit of history here. In the past, one of the popular methods was to use an EEPROM to store the program memory, and to erase the EEPROM you would require a source of ultraviolet light. So, to erase it you would have a box which had a UV lamp, with the lid, you put your EEPROM inside it. It would have a timer to say 15-20 minutes of dosage of the UV light required to erase the contents of the EEPROM. EEPROM typically would have a window. So if this is your IC and these are the pins, I am just drawing it for the sake of reference. You would actually have a window. This is a quartz glass window. Why quartz? Why not normal glass? Because normal glass absorbs UV light, and so these windows were made out of quartz glass, which is an expensive type of glass, which is why these ICs were also very expensive, but there was no other option, and so they would use a EEPROM to first erase it and then put it in a special system, special programmer connected to your PC through some protocol. On this programmer you would have a socket with a lever, where you raise the lever, it opens up the pins, you drop the EEPROM into the pins of the socket and then you press that lever. That special socket with something like this, these were the pins of the socket. This was a special socket, this is still in use in test equipment, is called ZIF socket, and it stands for zero insertion force type of socket. Why? Because if you put a regular socket and you were to insert an integrated circuit in and out of it tens of times or 100 times a day, that socket will go bad. It will not make connection appropriately with the pins and may not be able to program it, and therefore you wanted a rugged socket which can take insertions and removals of external ICs hundreds of times a day over several years of its operation, and therefore a special socket was used, ZIF socket. So you would have this EEPROM programmer or a device programmer with such a socket. You would insert your EEPROM into the socket after you have erased it, then you would burn the program into the EEPROM, then you would take the EEPROM out of it and put it back into your target system and test it, and if it didn't work, again you would repeat this cycle. So obviously it was a slow process of compiling and downloading program into the memory of the microcontroller. In the mid 90s, there was introduction of a special type of E2PROM memory which was called flash, and the flash memory started getting integrated into microcontrollers for the program memory, and that allowed a user to program these memories without having to take it out of the system. Without having to take the microcontroller out of the system, you could program it using a feature called ISP, that is in-system programming. To offer in-system programming, some communication interface was required, and the most popular interface that is used is the SPI bus. We have seen that SPI is one of the communication protocols that is available on almost all varieties of microcontrollers, and so this was used to implement the ISP functionality. In more advanced microcontrollers, they would have a JTAG, Joint Test Action Group Protocol, which had dual use. One of the use would be to program the internal memory, and the other would be to use it for testing the microcontroller using the on-chip debugger that I mentioned. Another popular protocol would be for testing would be serial wire debug. This is a more efficient protocol which uses less number of pins than the JTAG. And another way to download program into your code is a method called in-application programming, meaning you don't even stop your application from running. While the system is running, you can download code into it using a technique called bootloader. Bootloader, let me illustrate that also. So the entire program memory of your system would be split in two parts. The major chunk of your program memory, this is your program memory. The major chunk of your program memory would be this one, which would be called user program memory, and a smaller chunk would be called bootloader program memory. And when you reset the system, it would normally go into the first location of the user program memory, but if the bootloader has been enabled, it would, the program counter will take the program and start executing the bootloader. The bootloader would communicate using a onboard communication protocol. It would communicate, and usually this communication protocol would be UART, or if it has USB, it would be USB, and it would try to establish a contact with the host computer. The host computer would have a corresponding program which would establish communication with the bootloader, and then it would transfer the memory bytes, the program memory bytes sequentially, serially, one after the other. The microcontroller bootloader program would receive it and would actually write into the user program memory. After the program transfer is complete, it would transfer the control to the first memory location of the user program memory, and user program execution would begin. This method is called in application programming and using the bootloader method. This is commonly used in your Arduino platforms, and lo and behold, the MSP430 lunchbox that you all are going to be working with also uses this bootloader method to download code from your PC into the memory of the microcontroller. MSP430 microcontrollers come with a default bootloader program loaded into the memory at manufacture time. So, we do not have to worry about having to write or load this program into the bootloader program memory area, and so it is a good to go system MSP430 as long as invoking the in application programming feature of MSP430, and we are going to use that. This completes the program download capability or rather the feature of microcontrollers, and you as a designer must select one or the other option so that you can download code from the desktop computer into the memory, so that your system can work. The development of that system can continue unhindered. The last part of the ecosystem is power supply. We are going to, subsequent to this, we are going to have a dedicated session on power supply design, including that for the microcontroller, but I thought I would use this opportunity to illustrate that on your microcontrollers, typically you would here you see two pins, DVCC and DVSS are two pins on MSP430, whereas on your AVR microcontroller, this is the AVR at Mega microcontroller, there are two sets of pins. As I mentioned earlier, this is the digital supply voltage, and this is the analog supply voltage pins which are available. You have to refer to the data sheet as to what is the supply voltage that the microcontroller expects. For example, MSP430, the expected supply voltage is 3.3 volts typically, whereas for MSP430, whereas for AVR microcontroller, it offers a wider range, anywhere between 3 volts to 6 volts they can operate, and therefore it becomes your responsibility as a designer to provide a smooth DC voltage of this or this value so that your microcontroller can function properly. When it has two sets of power supplies, as in the case of AVR, one for the digital pins, digital part of the circuit inside the microcontroller, and the other for the analog part of the microcontroller, then one has to deal with that situation a little care, with little more care. If this is DVCC to represent the digital input, One very good method is first of all to put decoupling capacitors, two decoupling capacitors connected in parallel, and the purpose is not to add the two capacitance values, which is what actually happens, but this is typically a 0.1 microfarad ceramic capacitor, and this could be a 10 microfarad electrolytic capacitor, and then this is your ground and this is your ground. So, I ground that pin, and if you have analog AVCC also you would connect a capacitor, two capacitors actually, and please note that I am actually using different grounding symbols to indicate that these do not share the same ground with the ground of the. So, this is, I would call it A, G and D, and this I am, you see, I am grounding like this. This could be plus 5 volt, this could also be plus 5 volt, but because I have connected the ground here separately, the source of the pins power supply is say plus 5 volts here, and this is my ground. The way to ensure that these analog grounds are not directly connected to the digital grounds on the microcontroller pin is to route them separately using separate tracks. Similarly, you have separate tracks to go here, these are all connected together and then they go here. If you keep the track separate, it would serve the purpose of isolating the noise which is often generated on the power supply pins because of the internal switching action in the logic circuit, and it will not corrupt this power supply voltage. How to achieve that in real life, in practical, we would consider when we are looking at system design issues, where we will show how to design a PCB from a from a schematic. What do you do to ensure that there are two parallel tracks, one for providing power to the supply to the analog voltage and the other to supply voltage to the digital part of the circuit. We will consider that, but this is an important point to keep in mind in case your microcontroller has separate pins for analog and digital components, subsystems within your microcontroller, that you design the routing, you design the PCB appropriately so as to do justice to the internal components. We will continue our discussions in the next lecture, where we will look at the design of power supply in more detail, and I will go through the various options that are available. Thank you for watching. Bye bye.